Good morning. I'm Glenn Healey, and this is Work with Aidan Seaman, Stephen Inglis. Quiet, please. Aidan Seaman, Stephen Inglis, Tristan Sandler, Matt Schaefer, and Ryan Reinsell at Yakkertech and Baseball Cloud. And I'm going to be talking about physical models for pitch trajectories, and in particular, a new model for movement due to the seam shifted wake force. And there's a lot of applications for these kinds of models. The ones we're going to focus on here are pitcher development, evaluation, and pitch design. Now, Alan Nathan wrote in one of his papers decades ago that pitching was largely the art of trying to control the flow of air around the baseball. And it took many years, but we finally were able to get pretty good pictures for what this looks like. And I'm going to show some pictures from John Garrett's master's thesis. You heard from him yesterday. And these are generated using particle image velocimetry. And the first picture here, we've got a non-spinning sphere moving to the left. And if we look, there's a point on the far left of the ball called the stagnation point, which is the point of maximum pressure. And then as we move away from that point, going both up and down, we get to a point of minimum pressure at both the top and the bottom. And then not far behind that point of minimum pressure, we get a separation point here on the top and bottom of the ball. And that's where the boundary layer separates from the ball's surface. And then behind that point, not far behind it, we get the wake, and the wake and the separation points are things that show up really well in these PIV images. Now, the idea is that the wake is at a lower pressure than the stagnation point, but at a higher pressure than the minimum points. And that gives us a higher pressure on the front of the ball, which leads to a drag force, which slows the ball down. Now, if we look at another picture, this time the ball is spinning clockwise, and that spinning causes the separation point on the top of the ball to move right relative to the separation point on the bottom of the ball. And that causes us to have a net greater pressure on the bottom, which forces the pitch to move up. That's called the Magnus force. And then the one we're going to be focusing on is the seam shifted wake. In this picture, the seam causes a separation point on the top of the ball. That causes us to have more of the wake at the top and overall higher pressure on the top, which drives the pitch down. Now, we can draw these forces on a picture that looks like this. Each one of these forces causes movement on a pitch. Here we've got an average changeup, major league changeup from a right-handed pitcher. We've got the effect of the drag force, the Magnus force, and the seam shifted wake force. Of course, the goal of a pitcher is not necessarily movement. The goal of a pitcher is to get people out, and not all movement is equally effective at getting outs. So we can look at pictures like this. This is a Lance Lynn sinker, and we're plotting vertical movement and horizontal movement. And what the colors show here is the value of the pitch, what are known as intrinsic pitch values. The big numbers here are good for the batter. These are proportional to run value, so big, good for batter, dark, good for pitcher, 0 is league average. And what you see, the first vector that goes to here, that is the movement from just the drag and the Magnus on the pitch. So that's in a pretty hot part of the plot here. So that's a very hittable pitch, good for the batter. And if we then add the seam shifted wake force, that brings the pitch down here into the blue area, which makes it a very good pitch. So the seam shifted wake is critical for this pitch. One thing you can see is if we added more Magnus movement, that would kind of push the vector up in the same direction. Doesn't help, might even make the pitch easier to hit. So it's not about movement, it's about getting the right kind of movement to get results as a pitcher. And that was just one example we can look at. This is the average intrinsic run value of the seam shifted wake force per 100 pitches. All of these are negative, meaning they're all beneficial for the pitcher. And some of them are close to a half or even greater than a half of a run per 100 pitches. So the point is seam shifted wake is very important for a pitcher's effectiveness. This is just for completeness. If you want to read more about these intrinsic pitch values, there's an article here and a Driveline put together a video about it. You can can also go watch that. Now, we were able to derive these intrinsic pitch values from the pitch FX and hit FX data that we had a number of years ago from MLB. Not long after that, well, quite a few years after that, actually, TrackMan came along with their radar and MLB. And the new thing that we got there was the spin rate. And having the spin rate allowed us to build better models for the Magnus force. And the Magnus force is described here, depends on the air density. We heard about weather earlier this morning, the ball cross-sectional area, the lift coefficient, and the velocity. This lift coefficient itself depends on what's called the spin parameter, the ratio of the spin rate to the velocity, and then the spin efficiency. The air density, again, just a slide here for completeness. The model that we're using is the reference in the middle. First author is Terry Bayhill. And for our work, we get the weather data from Weather Underground. And what we've been able to do, as far as the Magnus force goes, is look at millions of pitches from TrackMan and come up with an improved model for, this is the lift coefficient versus the spin parameter. If you want to read more, the reference is on the bottom here. But what we had before going into this work is a number of lab type measurements. The black and the red spots here are individual pitches that were measured. And then if we look at these blue spots, each one of these represents statistics computed over hundreds of pitches for pitchers, pitch types, and seasons. So a lot more data goes into those. And the idea is we're trying to find a bounding curve to these points. And you see that there's quite a bit of these light blue TrackMan points in between the previous model and the new model, which gives us something that's a lot better for the Magnus force for major league pitches. And one of the things we've learned is it's very important to do these laboratory experiments, these controlled experiments, then to really dial in these models, we want to take lots of pitches, lots of data as much as we can, because things like how a baseball moves is very complicated. We're only going to be able to do so much if we have very small types of experiments. Okay, and one of the other things that came out of this that really required having millions of pitches is we could model the dependence of the movement and the lift coefficient on the seam height. Even looking at changes in seam height down around even less than 1,000th of an inch. Eno wrote about this in The Athletic if you want more details on that. Okay, so after TrackMan, we in 2020 got the Hawkeye optical system. And the new thing that we got with Hawkeye was information about the three-dimensional spin vector. And once you have the three-dimensional spin vector, you can predict the direction of the Magnus force. And one of the things that people discovered very quickly is that the direction that the ball should be moving in, according to the Magnus force, is not always the direction that it actually moves in. So that gave people the very clear understanding that this seam shifted wake effect was real, and they started trying to study it with quite a bit of energy. And we saw this one before, so what I'm going to add here to this picture is this vertical line you see. This represents what's called the hemisphere plane. And this is a plane that goes through the center of the ball and is proportional to the velocity direction. And one of the things that has come out of the Utah State work is that most of the separation activity occurs fairly near to this hemisphere plane. Now, in order to be able to model what's happening with these seams causing these separations, we need to be able to know where the seams are. And so luckily, these optical systems are now able to measure what's called the seam orientation. And that might be an unfamiliar term. So we've got a precise definition here. Seam orientation is the location relative to the seams where the spin axis pierces the surface of the ball. So if we look at these two pictures, they have exactly the same spin vector or spin axis. That's the blue vector in the two pictures. But what you see is that spin vector pierces the surface of the ball in different places compared to these seams. And that's going to cause the pitch to move differently. And so it's very, very fortunate that we can now measure this and make these predictions. And you might ask, how do we specify the seam orientation? Well, we specify it relative to a standard ball configuration. This here is the standard configuration where you can read the writing. And And if we look at the Yakutech optical ball tracking system, it's able to measure the seam orientation in terms of two angles. So the writing on the ball would be here, and they specify a latitude is the red and the longitude is the green that get us to the spin vector. So that's one way to do it. And there's a technical report that Aidan wrote at the bottom that you can go read if you're interested in more details on that. And then you might have seen these mallweed projections that Tom Tango has been putting out on Twitter. This is the same idea. He gets these from Hawkeye. It's a little bit different representation, and then you take the 3D sphere and you unwrap it into a flat 2D ellipse, and then you can specify XY coordinates on the ellipse to tell you what the seam orientation is. So it's another way of doing the same thing. Now, most baseball fans probably know we have 108 stitches on the ball. So what we do is to figure out where the stitches are, we have a parametric model. The reference here is at the bottom. And in order to specify the parameters, we take some high resolution images and we get the parameters of the model here. If you're going to use something like this, if you sample uniformly in the parameter here, T, they don't give you uniformly spaced samples on the surface of the ball. So you want to do a little bit more work and get them uniformly sampled in 3D. And one of the nice things from this model is we can compute the derivatives, and that tells us the orientation of the individual stitches as we move around the ball. And that's going to be important for the seam shifted wake model. Okay, so here is our seam shifted wake force. The magnitude, again, depends on the air density, the cross-sectional area, the seam force coefficient CS, and the velocity. And the CS is kind of the important function that we have to try and model. And it's tricky because this CS function depends on where every seam is at every instant of time and the angle that seam is at every instant of time. And as the ball is spinning, this seam force coefficient function is changing. And what happens is any individual seam, as the Utah State work showed, at any instant of time might cause a separation. It might not. It's a probabilistic thing. And where the seam causes a separation might not be at the seam. The seam might just disrupt the airflow enough to move the separation a little bit downstream, but off the seam location itself. And where the seam happens to cause a separation determines the amount of the force on the ball. So the further forward that the separation occurs, the greater the force. So we have to somehow account for all those things. And what we're going to do, the only unknown here is this seam force coefficient. So we're going to learn it as a function of a couple angles that I will define and the spin direction. And the direction of the seam shifted wake force is given by this triple product on the bottom. If you're not good at triple products, what this is, the S hat here is the vector from the seam point to the center of the ball. And then this triple product is the projection. It's actually the negative of that projection onto the hemisphere plane. So bottom line, points on the top of the ball will tend to drive it down, those seam points. If you have, say, seam points on the right side of the ball, that'll push it to the left. So the force always moves opposite where the seam point is. The hemisphere plane angle we define like this. The hemisphere plane is the vertical line through the center here. And if we take any seam point, draw a vector from that seam point to the center of the ball, we can take the angle of that with the hemisphere plane, and that's this HP angle. We call it positive on the front of the ball, the velocity side, and negative on the other side. And then we also define the seam angle that we can get from those derivatives, and that's the angle that the seam makes with the velocity direction. So we're assuming here the ball's moving up. So on the left picture, the seams where I've drawn the line, those are at 90 degrees to the velocity. And then on the right, those seams are at 0 degrees. And the idea is that it's harder for the airflow to negotiate the surface of the ball on the picture on the left. So at 90 degrees, there's a bigger bump that the air's got to go over. So there's a higher probability of getting a separation. All right, so we put all this data into thousands of pitches into some fairly advanced machine learning and estimation methods. And we get the CS function that's given here. And what this is showing is for any HP angle and seam angle and direction of spin, what that seam force coefficient is. So if we take any point in the circle and we draw a line from there to the center, the angle that makes with the vertical is the hemisphere plane, is the HP angle, and then the seam angle is represented by distance from the center. So the center of the circle is a seam angle of 0, and then the edge of the circle is a seam angle of 90 degrees. And if you look at this, similar to what the Utah State people found, most of the activity is near the hemisphere plane. Okay, the brighter colors are bigger values of CS. The maximum in this distribution is at about 10 degrees in front of the hemisphere plane. That's where we want the seam for maximum effect at a seam angle of 90 degrees. And then this is for the seam point spinning into the velocity direction. At the bottom, we've got the seam point spinning away from that direction. And on the bottom, the peak is about 3 degrees. So there's about a 7-degree shift between rotating into the velocity or rotating away from the velocity direction. You might expect that because for the points rotating into the velocity direction, there's more friction with the airflow going across the ball. All right, so now that we've got this, we can put this into the seam shifted wake model, and we can now predict movement for any pitch given the release parameters and the seam orientation. And I want to show you some examples of doing this with the baller visualization tool from Baseball Cloud. The first pitch here is a curveball from a right-handed pitcher, 78 miles an hour, and the sensor measures a total horizontal movement of 9.3 inches glove side and a vertical movement of 5.2 inches down, which are fairly reasonable for a curveball. And then when we isolate the seam shifted wake movement, the sensor and the model both predict between 4 and 5 inches of glove side horizontal movement just from the seam shifted wake, and a smaller, about 0.6 inches vertical movement up. And I'm going to show you a few videos, but I'm first going to just show you some frames from the videos so you know what to look for in the videos. The first one, we're just going to have the ball spinning, and this is a fairly typical, this is from the catcher's point of view, fairly typical spin vector for a right-handed curveball. The one in the bottom left, we're going to show you from the pitcher's point of view, the ball spinning, but now the ball is transparent so that you can see the seams on both sides of the ball. And we're going to color each seam according to the seam shifted wake force that it generates. So this pitch is moving to the left, glove side from the pitcher's point of view, which means that we're going to see as the ball spins that there is going to be more force. So the brighter colored seams are going to be on the right side of the ball, pushing it to the left. Now, a lot of pitches, when you look at these visualizations for the seam shifted wake, there's force on the top, on the bottom, on the left, on the right. They all kind of cancel out. You don't get a lot of seam shifted wake movement. The ones I'm showing you, you do get quite a bit of movement. So look for the seams on the right here. And then the bottom right, for this video, we're going to show you the pitch viewed from the third base side. And this is where most of the force is coming from. So we're going to see how the seams kind of line up. You've got the vertical line here is the hemisphere plane. And you can see this is a good case for seam shifted wake. You've got this nice row of seams just in front of the hemisphere plane, on the plate side of the hemisphere plane, which is where you want them. And they all have seam angles that are pretty close to perpendicular to the velocity direction. So you can really visualize what the seam shifted wake is doing. Okay, so let's run this. This is just the ball spinning. So fairly typical curveball spin. The magnets will move it down and away from a right-handed batter. And it's not giving me the next slide. Okay, there we go. So this is the one where we can see through the ball and look at the seams. Oops. And we're looking for the force to be the bright colored seams on the right side, which is what's driving the ball to the left. Of course, the computer is computing these things as you go. If you have really good eyes, you might be able to see there's a little bit more force on the bottom, which is driving the pitch upward. So we can visualize what each seam is doing as far as the seam shifted wake. And this is the third base view of the same pitch. And you can see here how the seams are orienting kind of in front of the hemisphere plane and lining up to give us a strong force on the third base side, which is driving the pitch back to the first base side. Okay, so I had one more example. This is a right-handed slider, 83 miles an hour. This one, the sensor has moving at 9.2 inches glove side and 4.8 inches up. The glove side is fairly reasonable for a slider, but 4.8 inches up is very unusual. And that all comes from the seam shifted wake. So we can look at this. The sensor and the model both give us about 2 inches of arm side movement. So the seam shifted wake here is causing the slider to back up, which you probably don't want. And it's causing it to move between here 5 and 7 inches vertically, which you also probably don't want out of your slider. I'll show you a picture of just the ball spinning. It's, again, fairly typical slider spin vector. Just the Magnus force is going to take it down and away from the right-handed batter. But the seam orientation is going to cause you to get this very unusual backing up of the pitch and vertical rise on the pitch. So then I'll show you the one on the lower left here, and you can see we get a lot of force on the left side, which is what is going to drive the pitch to the right, and a lot of force on the bottom of the ball, which is going to drive it up. And then the final video, the one here in the bottom right, is from the ground looking up. We can look at the bottom of the ball, and we're going to see how the seams line up on the bottom to give us force that pushes the ball up vertically. And you can see here the catcher's at the bottom of this one, that direction. So we got these seams lining up just, again, a bit in front of the hemisphere plane with angles that are reasonably close to perpendicular to the velocity direction. Okay, so the first one is just this is just the slider spinning. Again, fairly typical slider spin profile. Again, move down and away from the right-handed batter, but the seam shifted wake causes it to do some things that are kind of unusual. And this is the one where you can see through the ball. So here we're looking to see the seams are mostly lit up for the seam shifted wake from the bottom, which is driving the ball up, and a little bit more lit up on the left side, which is causing the movement back to the right. And again, if you can't, hopefully you can see these things in these pictures, but the computer's determining the exact movement from how these seams are changing as the ball is spinning. And then the last one, this is looking from the ground up, and you can just see a lot of the force where it comes from the various seam points, and that's what's giving this slider this very unusual upward vertical movement. Okay, and that's it. So we have a new predictive model for movement due to seam shifted wake. You can put in a pitch with its seam orientation and the release parameters and predict the movement, and then you can predict the value of the pitch. So you can take pitches that are thrown, try to improve them, or you can just go through and if you want, just search for pitches that give you certain kinds of movement profiles, figure out what sorts of seam orientations you would need to make the pitch do whatever you might like. And we've shown how we can use this for pitcher development evaluation and for pitch design. So that's it. If we have time, I can answer any questions. Nope.